Welcome to the lecture of Professor Carsten Thomassen. So it's a pleasure for me to introduce Professor Carsten Thomassen from Denmark. So as he told me, this is the second time that he comes to Brazil, so we have to invite him more times. So Professor Thomassen got his PhD in '76 from the University of Waterloo, and so only 5 years later he became full professor at the Technical University of Denmark, so very young full professor, and some years later he became member of the Royal Danish Academy of Science and Letters. Well, there is a lot to say about Professor Thomassen, but I shouldn't take so much time. But so his contributions are in discrete mathematics, more specifically in graph theory. He has more than 200 papers in many different topics. Almost any topic you think of in graph theory, he has some big contribution, some big theorem that you have to mention. So that varies from Hamiltonicity, hypohamiltonicity, decomposition, coloring, least coloring, and graphs on many surfaces, and almost anything, reconstruction, crossing numbers. So it's a very huge contribution in many different areas. And currently he's the editor-in-chief of Journal of Graph Theory and a member of the editorial board of many other journals like Combinatorica, Journal of Combinatorial Theory, Discrete Math, Journal of Electronic Combinatorics, and so on. So, and in terms of prize, awards, recognition, there are a number. I'll just mention some. So in 1990, he was the invited lecturer at the ICM, International Congress of Mathematicians in Kyoto, and he got many other prizes in the States, Canada, France. So there, you could see in his page there are a number of them. Today he's going to talk about a contribution, a recent contribution he has in integer flow theory, but his contribution is so huge. But it's very nice that today he'll talk about these recent contributions. Very nice, and so today we'll have these opportunities. So, Professor Thomas.
Thank you very much for the generous introduction. Thank you very much, and also thanks to the organizers for having invited me to this interesting conference in this beautiful city. I would like to talk about, as it has been mentioned, orientations of graphs. So let me start by defining a graph, although that's probably not necessary, but just to make the notation clear. When I say graph, I mean a finite graph. I mean a finite undirected graph. We have a finite set of vertices, we have a finite set of edges, and every edge joins two vertices. We may have multiple edges. We may have edges joining the same two vertices. We may even have edges like this, we call loops, but they will play no role in what I'm saying. But multiple edges do play a role. So when you have a vertex and look at the number of edges going out from the vertex, I call that the degree. Some people call it valency. And then I'm going to put orientations on the edges. I'm going to make every edge a directed edge. And when I have done that, I call that an orientation. And I'm also going to put numbers or group elements on the edges. So let me say more clearly what type of problem I would like to talk about. Let us consider a group gamma. It's abelian. And let us take a set of group elements, all different from 0. And let's consider a graph G. now we ask the question, can we give every edge an orientation and a group element from F in such a way that at every vertex the inflow is equal to the outflow? So if you look at a vertex here, we have a vertex of degree 3. For this vertex, we have the equation that the incoming edges x3, x5, when we add them together, we get the same as when we add the outgoing edges together. So that's a very general question. For every group, for every set of elements in the group, and for every graph, we have a problem. And is it easy to decide, or is it difficult to decide if we have such, I call it an F-flow. Let me look at an example. Here we have the prism, and I have put elements on and directions on the edges. And here we have 6 equations. But we can combine these 6 equations to get some other interesting equations. Here is what we call a cut. If you divide the vertex set into 2 parts and look at all the edges between the parts, we call that a cut. So for example, here we have a cut consisting of these 3 edges. And we also have an equation for these 3 edges. So the initial condition is that every vertex should be balanced. The inflow should be equal to the outflow. But it turns out that also for every cut, we get an equation. Every cut must be balanced in the sense that the flow from left to right is the same as the flow from right to left. And that's easy to see because let's look at all the vertices on the left side. For each of them, we have an equation. So for example, here, x1 plus x4 is equal to x2. Let us write it in this way so that we have 0 on the right-hand side. We do that for all vertices on the left side. And then we add these equations together, and let's see what we get. Well, if you focus on x1, for example, you'll see that it appears twice, x1 here and x1 here, and with a minus. So these 2 cancel. So all the edges in joining vertices on the left-hand side, they cancel out. And the only thing you get is a contribution consisting of x4, x3, and x5, and you get this equation, x4 plus x3, so that's the flow from left to right, is equal to x5, which is the flow from right to left. And we say that this means that this cut is balanced. Every cut must be balanced if we have such a flow. And this has a consequence, namely that every cut must have at least 2 edges. If the flow from left to right is equal to the flow from right to left, every cut must be balanced. I'm not saying that there must be edges from right to left, because that's not the case. I mean, it is possible that all edges go from left to right, but these flow numbers added together should give 0. And this is not possible if you only have 1 edge. Because remember, I assume that 0 is not a flow value we can use. And the reason why it's not a flow value we can use is that if we could use it, it would be very easy to satisfy all these equations. The problem would be trivial. So we have now seen that if we have a flow, we must have the condition that the graph has no cut consisting of 1 edge. Such a thing is called a bridge. And we also say that a graph with this property is 2-edge connected. Every cut has at least 2 edges. The graph is 2-edge connected. I'll say a little more about edge connectivity. The edge connectivity is a measure of how well the graph hangs together. There is a similar concept of vertex connectivity. I'll not come into that. So here the first graph is connected. And we also say it's 1-edge connected because the smallest cut has 1 edge. The next graph is 2-edge connected because here every cut has at least 2 edges. And we have many cuts with precisely 2 edges, this one, etc. And then the last one, the prism graph, that is 3-edge connected. So the edge connectivity is the size of the smallest cut. It can also be proved that it's the size of the smallest edge set you must remove if you want to make the graph disconnected. So let's look at let's look at the simplest case. Sorry. The simplest case is when we only have one available flow value. Let's consider the integers and one available flow value. We could say it's 1. So here we seek an orientation such that at every vertex the in degree is equal to the out degree, because we can forget about the flow value. If there is only one flow value, that's the condition. The in degree should be equal to the out degree for every vertex. And it's easy to decide when that is possible. Because if you have in degree equal to the out degree, then of course this vertex must have even degree. Every vertex must have even degree. We call that an even graph, or sometimes an Eulerian graph. I'll call it an Eulerian graph. So let me give the argument that conversely, if we have an Eulerian graph, then we can find an orientation such that at every vertex the in degree is equal to the out degree. The proof is very easy. So here is the proof. We start by selecting any edge. Now we select an edge going from this vertex, an edge going from this vertex, and we can always do that because no vertex has degree 1. We have an even graph, an Eulerian graph. Every vertex has even degree, so we can continue, and we stop when we get a repetition. What we have formed here is what we call a cycle. We have formed a cycle, and what I do with this cycle is that I make it into an oriented cycle, like this. I make all orientations go the same way, clockwise, and then I delete the edges of this cycle, and I still have a graph where every vertex has even degree because I steal 2 edges from every vertex. So I can iterate. Oh, thank you very much. So that was an easy example when we have only one flow element and we are working with the integers. But if we change the group, the problem changes very much. So the second simplest case is when we still have only one group element, but now our group is set 3. The integers reduced modulo 3. So here we also want every vertex to be balanced. But balanced means something else. It means that the in degree is equal to the out degree modulo 3 at every vertex. So this could be 1 in and 4 out. And actually, that's where the problem lies. If all vertices have degree 5 and you want 1 in and 4 out, or 4 in and 1 out at every vertex. That's a difficult question. It's a so-called NP-complete question. This means that it's probably hopeless. We cannot find a good algorithm for solving this question. We cannot find a good characterization of the graphs which do not have such an orientation. And this leads to a famous conjecture, Tutt's free-flow conjecture. When Tutt formulated his free-flow conjecture, he didn't do it this way. He looked at another situation, namely the case where we now go back to the integers, but we look at the 2 group elements 1 and 2. And that is Tutt's free-flow conjecture, which is over 40 years old. He conjectured that if a graph is 4-edge connected, so no cut with 3 or fewer edges, if the graph is 4-edge connected, then G has a 1-2 flow. And that is also sometimes called a nowhere 0-3 flow. What about this number 4? Is that best possible? Yes, it's best possible. There are many graphs showing that 3-edge connected is not enough. The simplest is K4, the complete graph on 4 vertices, the tetrahedron. That has no 1-2 flow. That's very easy to see, because if you try to find a 1-2 flow, then at every vertex you must have 2 incoming edges of flow 1 and 1 outgoing edge of flow 2. But then at this vertex, you must have 2 outgoing edges of flow 1, so 1 and 1, But then you see you have a problem with the last edge. You cannot give it any flow. You have to give it flow 0, and that's not allowed. So 3-edge connected is not enough, but 4-edge connected is believed to be enough. And why this conjecture? Well, it was inspired by a classical theorem of Griggs, a coloring theorem, a theorem about the chromatic number. And many flow problems stems from chromatic graph theory. So Griggs' theorem says the following. If you have a graph which is planar and triangle free, planar means that you can draw it in the plane such that no two edges cross. And then it should also be triangle free. Then the chromatic number is at most 3. And let me explain what the chromatic number is. Now you give every vertex a color, which could be a number. I like the colors 0, 1, and 2. So you give every vertex a color, and the rule is that neighboring colors should have different colors. You are allowed to use the same color many times, but not for neighboring vertices. So here is an example, the Pentagonal Prism. I have shown a 3 coloring. And that 3 coloring shows that the chromatic number is at most 3. If you use the smallest number of colors, we have the chromatic number. So the chromatic number is at most 3. Actually, here it is 3. You cannot do with 2 colors, because if you have a pentagon, you cannot color that with 2 colors. You would have to use color 0, 1, 0, 1, 0, 1, and that doesn't work with an odd cycle. So the chromatic number of this graph is precisely 3. And every planar triangle-free graph has chromatic number at most 3. Maybe I should mention now that you might try to generalize this to non-planar graphs. What about a non-planar triangle-free graph? Will that always be 3 colorable? Can that be colored with 3 colors? No. You could then ask, can it be colored with 100 colors? That's not so easy to see, but the answer is still no. There's no hope of generalizing this to non-planar graphs that are not drawn in the plane. But in the plane it's true, and let me point out that this theorem proves the 3-flow conjecture for planar graphs. Remember, the 3-flow conjecture says that you can give every edge an orientation and a number 1, 2, such that every vertex is balanced. So let me prove this now using Griggs' theorem for planar graphs. We have now a planar 4-edge connected graph. When you have a planar graph, we can define the dual graph in the following way. Think of it as a map, then in every country, we call it also a face, you put a vertex, and then you draw edges between neighboring countries. That's called the dual graph, and the dual graph is also a planar graph. And I miss a couple of edges. If you take the dual graph of the dual graph, you come back to the original graph. So that's the dual graph. So now let us look at a planar graph which is 4-edge connected. If you look at the dual graph, you can think of the dual graph as the vertex set of the dual graph you can think of as the countries. So when you color the vertices of the dual graph, you color the countries. And the dual graph here has no triangle. So by Griggs' theorem, it can be colored with 3 colors. So the countries can be colored with 3 colors. Let's do it. And let's look at what happens locally around a vertex. So for every edge, I now give the edge the orientation so that you have the largest color on the right-hand side. I use colors 0, 1, and 2. And I will always have the largest color on the right-hand side, and then I take the difference between the 2 numbers, and I give the edge that number. So here I give it number 1, here number 1, and here 1. And then you see that the inflow is equal to the outflow. I hope this is true. It doesn't look. Oh, there's one edge missing. So it should be on the right side. So I hope it's true now. So 1, 2, 3 in, and 1 plus 2, that's 3 out. And that always happens. So we have now seen that the three-flow conjecture holds for planar graphs. And you can do that with other chromatic numbers. We have the five-color theorem for planar graphs. If you have a planar graph, then the countries can be colored in 5 colors, such that neighboring countries always have different colors. This has been known for over 100 years. And then we have the much, much stronger thing that you can, in fact, do with just 4 colors. That's the famous 4-color problem, which is now a theorem. But using the 5-color theorem, you can get a 1, 2, 3, 4 flow of any planar graph. And using the stronger 4-color theorem, you can, in fact, get a 1, 2, 3 flow for every planar graph. Can these be generalized to non-planar graphs? And it turns out that there is a good hope of that. So here is Tutt's famous 5-flow conjecture. He conjectured that every 2-edge connected graph has a 1, 2, 3, 4 flow. You can put numbers 1, 2, 3, 4 on the edges, and that's a strengthening of the 5-color theorem for planar graphs. If you could get rid of this number 4, then you would have a very strong theorem, because that would imply the 4-color theorem. Unfortunately, that is not possible. And the smallest counterexample is the famous Peterson graph. Maybe I can draw it. So I have already mentioned a graph which has no 1-2 flow. And it's the smallest graph which has no 1-2 flow. And then we also have a graph with a no 1, 2, 3, 4 flow. No, sorry, 1, 2, 3 flow. Namely the Peterson graph, which is the following. You take a pentagon, and then another pentagon, 2 pentagons joined by what we call a perfect matching. This one has no 1, 2, 3 flow, and it's the smallest example. You could say it's the smallest counterexample to the 4-color theorem for planar graphs, and that's why Peterson constructed that graph. By the way, Peterson was a professor at the same university as I'm professor, but many years earlier, of course. Now, when Tutt made his conjecture, it was not even known if you could get a 1, 2 up to k flow for a fixed k. It's easy to see that for every graph you can find a 1, 2 up to k flow for some k, but can you use the same k for all graphs? Even that is not trivial. Can you prove it if k is 1,000? The answer is yes, and this was first proved by Teixeira, and he could actually do it with the numbers 1, 2, 3 up to 7, and that's called a nowhere 0, 8 flow. And I would like to show Teixeira's argument. It's a very pretty argument, and this is from the late 70s, around 1980. So here is Teixeira's argument. First, he proved that if you have any graph, and as I have said, all my graphs are 2-edge connected. So we have a 2-edge connected graph, then you can write it as the union of 3 graphs, G1, G2, and G3, in such a way that these 3 graphs are all Eulerian. In these 3 graphs, all the edges have even degree. So it's not a decomposition of the graph, because an edge may be in 2 or even 3 of these graphs. Now, but it is true that you can find such a covering, we call it, of a graph. And Teixeira used matroid theory to prove this beautiful result. Now let's take these 3 graphs and let's give G1 a 1 flow. We have seen that this is possible. The argument was trivial. But we can, instead of using the number 1, we can also use the number 2, and we will do that for all edges in G2. And we will use the number 4 for all edges in G3. And then we add these flows together. And let me explain what I mean by adding flows together. Let's focus on an edge xy. It may be in G1, and it may have, for example, have the flow 1 in G1. It may be in G2, and maybe it has the flow 2, and so it has the flow 2 in G2, and maybe it's also in G3, and then it will have the flow 4 in G3. And then we add them together, but we respect the orientation. So here we say 1 minus 2 plus 4, that is 3. So that will be the flow value. And that will give us a flow, and which you never use the number 0, because 1 and 2 and 4 cannot be combined to get 0. And what is the biggest number you could get? Well, if these three work together, it's 1 plus 2 plus 4, so you could go up to 7. So this beautiful argument gives you that every two-edge connected graph has a flow using flow values 1, 2, up to 7. And the big problem is, can this be reduced? There is a famous result improving this, namely Seymour's 6-flow theorem. He reduced it not only by 1, but by 2. So he could do it with just the numbers 1, 2, 3, 4, 5, and that's a 6-flow conjecture. So we call it a 6-flow. The number 6 is the smallest integer greater than the largest flow value. So if we raise the edge connectivity, then Teixeira's argument gives the following, that every 4-edge connected graph has a 1, 2, 3 flow. And remember, in the 4-color theorem, it's 1, 2, 3 flow. So for non-planar graphs, for all graphs, we get such a flow, but we have to raise the edge connectivity a little bit to 4. And that is best possible because of K4, the tetrahedron. And the reason that this is true is that if you have any 4-edge connected graph, then it can be written as the union of 2 Eulerian graphs, and then we just repeat Teixeira's argument. We can also look at other possibilities. There is a conjecture called there was a conjecture called the 2 plus epsilon flow conjecture by Godin and Seymour. If you look it up on Google, it'll tell you that almost nothing is known about this conjecture, but that's not completely precise, as I will show. So the conjecture says that G has a flow where the flow values are between 1 and 1 plus epsilon, where epsilon is a small positive number, provided that the edge connectivity is large enough. So if you have large fixed edge connectivity only depending on epsilon, the conjecture says that you can find a flow with these values in this little interval between 1 and 1 plus epsilon. And of course, you can ask the more general question, if you have large edge connectivity, does the graph then have an F flow for any subset of elements in a group? Let me point out why edge connectivity is the relevant concept here. Let's look at a graph and let's look at a cut and assume that we have a flow. If the graph is Eulerian, then all cuts have even size. But usually graphs are not Eulerian. So if you have an odd cut, let's look at what happens with this cut. We have seen that we have an equation for this cut, namely that the edges from left to right, here x1 plus x2, the flow from left to right is the same as the flow from right to left. And that gives you an equation where you have an even number of elements on one side and an odd number of elements on the other side. So that condition must be satisfied. I call it the odd sum condition. So the odd sum condition is a necessary sufficient for having the flow. And now we can ask, if we have the odd sum condition and large edge connectivity, because we must also have large edge connectivity. If we go back to the interval between from 1 to 1 plus epsilon, then with those numbers you can satisfy the odd sum condition, but you must use a lot of numbers here. It must be a big equation, and therefore this cut must be big. So you must have large edge connectivity. And now the main theorem that I will talk about, we can indeed find such a flow. Now let's take a group. Let's take any set of elements in the group. It need not be finite. But we will assume that the odd sum condition is satisfied. Then if the graph is 3k minus 1 edge connected, the graph has an F-flow. So the connectivity is not that big, it's just a linear function of the size of this equation. And this has many applications. Let's look at the following example. Let's look at the example where our group is now the rational numbers with addition, and the two group elements are 1 and 1 plus 1 over k, where k is a natural number. Here we have the odd sum condition, because if you take k plus 1 of the ones and you take k of this number and add them together, you'll see that the equation is satisfied. And the two numbers k and k plus 1, well, one of them is even, one is odd, so that is the odd sum condition. And therefore we get the following. If G is 6k plus 2h connected, then G has such a flow. And this proves the 2 plus epsilon flow conjecture, even using just two flow numbers. I mean, Seymour and Godin allowed us to use all the numbers between 1 and 1 plus epsilon. But I just use a number, natural number k, which is so big that 1 over k is smaller than epsilon, and then we can just do with those two flow numbers. Let's look at what it implies for the graph. It implies that every cut is almost balanced. Now, by balanced, I now mean that the number of directions from left to right is almost the same as the number of directions from right to left. If I have chosen k big, because the sum of these flows should be the sum of these flows. But if 1 and 1 plus 1 over k are close to each other, then this also means that the number of these edges will almost be equal to the number of these edges. They will just differ by a small fraction. I mean, the ratio will be close to 1. So every cut is almost balanced, and this again means that as I have mentioned before, every odd cut is big. Conversely, one can prove, this has been known for a long time, that if you can find such an orientation, if you can always find an almost balanced orientation, if you can always make a graph almost balanced, then you can also find a 2 plus epsilon flow, a flow where all the flow number values are between 1 and 1 plus epsilon. And that was, in fact, the motivation for the conjecture. There are many, many other ways of proving this 2 plus epsilon flow conjecture. Let me take what I call a curious example. I take now 3 flow values, the flow value 1 and alpha, where alpha is an irrational number, and then alpha plus 1 over k, where k is a natural number. Again, we have the odd sum condition, because if you take 1 plus k of the alphas plus k of the last number, then the equation is satisfied. And we get the result that if you have a 6k plus 2h connected graph, then the graph has a flow using only these 3 numbers. And you can choose alpha close to 1, and you can choose k big, and then you have a new proof of the 2 plus epsilon flow conjecture. But here an interesting thing happens, namely that when you use flow numbers, you give every edge a flow. You could think of a flow as a color. So you give every edge a color. And we have a coloring such that in every odd cut, you see all 3 colors. And I have the feeling that there must be some structural consequences of this, but I have not found them. I would like to indicate a proof of the F-flow conjecture. And the proof comes from the fact that there is a connection with F-flows and then orientations modulo k. And let me mention one such connection. For example, a 1-2 flow, that's the same as an orientation such that every vertex is balanced modulo 3. At every vertex, the in degree is equal to the out degree modulo 3. And let me indicate how the proof goes. Suppose you have a vertex with incoming with 1 coming in and 2 going out. So we have a 1-2 flow. Then what I do is I ignore all the flow values. But whenever you see a 2, you reverse the arrow. And if you do that, you will see that you get this, that the in degree is equal to the out degree modulo 3. And conversely, if you have such an orientation, you can transform that to a 1-2 flow. So this was the first example, well, the second example, the first non-trivial example I mentioned. This was the third example I mentioned, but these two are equivalent. I proved a few years ago that if you have an 8-edge connected graph, then it has such an orientation. It has an orientation where the in degree is equal to the out degree modulo 3. So that proved what was called the weak 3-flow conjecture. Remember in Cicier's 3-flow, in Tutt's 3-flow conjecture, we talk about the number 4-edge connected. But then Cicier immediately thereafter made the weaker conjecture. Instead of 4, can we use a big number, for example, 1,000? And the answer is we can use, in fact, 8. Can 8 be reduced? Yes, a little later in a paper with Lobas, Xiang, and Wu, we proved that, in fact, 8 can be reduced to 6. Every 6-edge connected graph has a balanced modular orientation modulo 3. We can actually do a little more. At every vertex, we can get any prescribed out degree modulo 3. So if you say that you want this vertex to have out degree 0 modulo 3 and this to have out degree 1 modulo 3 and continue like that for every vertex, yes, we can find the orientation. But we need the edge connectivity 6. And now we are only one step away from Tutt's 3-flow conjecture, because if we can lower this 6 to 5, it can be proved that you can then also lower it to 4. We get every second one for free. And in this version, 6 can only be improved to 5. It cannot be improved to 4 if you prescribe all the out degrees modulo 3. It's not only modulo 3 which is interesting. Here is a conjecture about modulo 5. Cicier conjectured many years ago that every 9-edge connected graph has an orientation which is balanced modulo 5. Actually, he also conjectured that every 8-edge connected graph has such an orientation. And then one can easily see that 7 will not be okay. But 8 might be okay, but I would like to focus on 9 here for the following reason. Because if you can prove this conjecture with 9, then as a consequence, you would get the 5-flow conjecture. And let me explain why. If you want to prove the 5-flow conjecture, you usually you do it by contradiction. You look at a smallest counterexample. And one can prove that in the smallest counterexample, every vertex must have degree 3. It's a so-called 3-regular graph, a cubic graph. And conversely, the smallest counterexample must also be 3-edge connected. So let's look at the smallest counterexample to the 5-flow conjecture and assume that we have this 9-edge theorem. I take my smallest counterexample and I triple all the edges, replace every edge by 3 edges. Then I apply the 9 conjecture to this graph, because this graph is 9-edge connected. The edge connectivity is multiplied by 3. And then when you look at these orientations, it might, for example, these edges might be oriented like this. Then you would put the flow number 1 here. And if these 3 go like this, then you would do this. And then you will see that you get a 5-flow. To begin with, you only get one which is balanced modulo 5, but it's easy to transform such a flow to one which is actually completely balanced using flow numbers 1, 2, 3, 4. you may wonder why I say 4, why don't I just say 1, 2, 3? But it turns out if you look at the proof and work modulo 5 and try to transform that to a real balanced flow, you will have to introduce the number 4 there also. So I repeat, 9 edge connected would be interesting. And when in the proof of the weak 3 flow conjecture, I also proved that this is true for 55 instead of 9. So a big gap between 9 and 55. But then in the second paper with Lovas and the others, we pushed it down to 12. So now we are not too far away from this 9 edge conjecture. But of course, the last steps are the most difficult ones. So maybe we are far away. There's something called Schicher's circular flow conjecture, which generalizes many of the things I have mentioned. I've talked about modulo 3, modulo 5, but Schicher made a very general conjecture that you take any odd natural number, and let us assume that we have a 2k minus 2 edge connected graph. Then he conjectured that you can find an orientation such that every vertex is balanced modulo k. The number of incoming edges equals the number of outgoing edges modulo k. I have already mentioned that he made the weak 3 flow conjecture. Can you replace 4 by 1,000 when k is equal to 3? And we know we can replace it by even 6. If you put k equal to 3 here, you get 4 edge connected. And you get modulo 3 here, and that is touch 3 flow conjecture. If you put 5 here, you get 8 edge connected. And you get modulo 5 here, and as I have just shown, that would imply the 5 flow conjecture. So this is an enormously strong conjecture. I mean, even the first 2 interesting numbers have been unsolved for 40, 50 years. We may also consider the weak version of this. Can we replace this number 2k minus 2 by some number? And I proved the following, that yes, you can replace it by 100k square. If you have that edge connectivity, then you can make every vertex balanced modulo k, and you can also do the stronger thing. You can, at every vertex, prescribe the out degree modulo k. And then in the paper with Lovas, Xiang, and Wu, we pushed this quadratic function down to a linear function, only 3k minus 3. And if we can push this 3k minus 3 down to 2k minus 2, we would have Schicher's 3 flow conjecture. But of course, that will be difficult. Now maybe I could indicate the proof of the F flow theorem. Let me mention how this can be done using orientations. I first said we take a group. We can, in fact, just do with a semigroup. We take a set of group elements and we assume that the odd sum condition is satisfied. Here I have mentioned the odd sum condition. And then I claim that there exists the smallest number, which I call little f of f gamma, such that every f edge connected graph has an f flow. And I prove that you can, in fact, do with at most 3k minus 1. So let me indicate the proof of this. So what we have is a 3k minus 1 edge connected graph. We want to find an F flow. Here we have the odd sum condition. Even if we are in a semigroup, I will write it like this. And we assume that our graph G is 3k minus 1 edge connected. Now I look at I'll prove it by induction. Induction on the number of edges. The base of the induction is when you have 2 vertices joined by a lot of edges. That's easy. Let's look at a vertex of smallest degree. And let me first consider the case where the degree is as small as the edge connectivity. The degrees are always bigger or equal to the edge connectivity. But let's consider the case that the smallest degree is precisely the same as the edge connectivity. Then I do the following simple reduction. I take this vertex of degree 3k minus 1, which is an even number. And I delete the vertex and replace all the edges by half as many edges as I've indicated here. This is called a lifting. and then I use induction on this resulting graph. And if this edge has this direction and the flow number x, for example, then I will take the two corresponding edges here and give them these directions and the flow value x. And you see this vertex which I deleted becomes balanced. But there is a little problem. How can I use induction? I must have large edge connectivity. And if you make this reduction at random, you will lose the edge connectivity. That's a problem. But there is something called Marder's lifting theorem saying that if you do this in a clever way, you can preserve the edge connectivity. That's a very useful theorem when you deal with connectivity, that you can in fact lift a vertex of even degree and preserve the edge connectivity. So that goes very nicely. That was when the vertex of smallest degree has degree 3k minus 1. Then I look at a vertex of largest degree. If it has degree at least 2 more than the edge connectivity, I do a similar thing. I just take 2 of the edges and lift them off like this and do induction by Marder's splitting theorem. So that was also easy. There is only one case which is difficult, and that is what always happens in problems of this type. The difficult case is when all vertices have degree precisely 1 more than the edge connectivity. All vertices have degree precisely 3k. If you try to prove the weak 3-flow conjecture, it is sufficient to do it for 5 regular graphs. If you want to prove the 5-flow conjecture, it's sufficiently to do it for 3 regular graphs. This always happens. So now we are stuck with this case. All vertices have degree precisely 3k. And the edge connectivity is 3k minus 1 at least. But now we use the weak circular flow conjecture, which is now a theorem, to orient the edges in such a way that all the out degrees are divisible by k. I could do that. I could prescribe all the out degrees modulo k, and I want them now to be 0. But this also means that the in degrees are divisible by k, because the degree, all degrees are divisible by k. Now I'm going to do further operations on the graph which will destroy edge connectivity. That doesn't matter. From now on, I don't need edge connectivity. So the proof is on this transparency. So we look at any vertex. It has out degree divisible by k and in degree divisible by k. Then what I do is I split this vertex into 2 vertices, one such that all edges go out, and another vertex such that all edges come in. And then I further split these vertices into many vertices such that all the vertices either have k outgoing edges and 0 incoming edges, or k incoming edges and no outgoing edges. Such a graph is what we call bipartite. We have 2 types of vertices, those vertices where edges go out and those vertices where edges go in. And every edge joins these 2 classes. That's what we call a bipartite graph. All vertices have degree precisely k. And now we use a standard theorem saying that if you have a bipartite graph where all vertices have degree k, let me indicate it on the blackboard. You have a bipartite graph such that with 2 types of vertices, vertices here and vertices here, and all the degrees are the same, well, then you can edge color the graph. You can give every edge a color. In this case, color 1, 2, 3. You can do that for every edge such that at every vertex you will see all 3 colors. That's a beautiful theorem. It's not difficult. It's a standard theorem, but it's very useful. And we use it here. And now instead of using colors 1, 2, 3 up to k, I will use these flow values. There are k of them. And when I use minus xi, which I'm not allowed to, I just replace it by xi, but I reverse the arrow. And now I have an orientation such that at every vertex, the sum of all edges going out is 0. Edges going out is equal to the sum of edges. I mean, the sum of edges going out in this situation is 0, and this means out is equal to in. Now that is for this reduced graph, but when we go back to the original graph, we preserve this. So that's the idea in the proof. And I don't have much time, but there are many interesting examples. Here is something which has been studied a lot, what is called nowhere zero gamma flow. We have a group gamma, and the allowed group elements, the allowed flow elements will now be all the group elements minus 0. That's called a nowhere zero gamma flow. And let us assume that the group has at least 3 elements. How can we use the previous theorem? Well, let's look at this equation. x1 plus x2 is equal to x3. We can solve that equation. That can be solved in any group, abelian group with at least 3 elements. Sometimes you can even let x1 and x2 be the same number. And when you have solved it, you have the odd sum condition. And if you have an edge connectivity, which is then in this case 8, you can find this flow. So this means you can find, if you have an 8-edge connected graph, you can find nowhere zero flows for any group. But this 8 can be pushed down in many cases. And maybe I should finish in a finite time. There is a beautiful observation by Tutt saying that if you look at a finite group, then the number of nowhere zero gamma flows in a graph depends only on the number of elements in the group. It doesn't depend on the group structure at all. This is a little surprising. So this means that you can work with your favorite group if you want to find these flows. So what Seymour's 6-flow theorem implies is that the edge connectivity for this nowhere zero gamma flow is just 2 for every group with at least 6 elements. So that solves almost this problem completely. But we have some interesting small cases. I have already mentioned that every 4-edge connected graph has a 1, 2, 3 flow, and this means that, so we have 4-edge connectivity here, and this, you can reduce this flow modulo 4, and then for the cyclic group with 4 elements, you get that the relevant edge connectivity is at most 4, and K4 shows it's at least 4. So it is 4 here. And you can also reduce this flow modulo 5, and then, well, 4 is also sufficient for this group, but maybe we can push this 4 down to 2, but that's the 5-flow conjecture. So only one group is left, namely the cyclic group with 3 elements, and here it is either 6 or 4, and it's 4 if and only if the 3-flow conjecture is satisfied. So this variant of the problem is solved completely, except for 2 details, namely the 5-flow conjecture and the 3-flow conjecture. I don't think I have too much time, but let me just say that there are some other interesting cases there. You could look at the case. Yeah, I'll just mention it. You could look at the case where the group are the complex numbers and the group elements are the 3 roots of unity. Well, that turns out to be the same as a 1-2 flow, so we are back to Tutt's 3-flow conjecture. You could look at the 5 roots of unity, and I'm not going into details now, but just let me mention that if you use the 5 roots of unity, edge connectivity 14 is enough. And if you take such a flow and ignore the flow values, you get a flow which is balanced modulo 5 if you think about it for a few seconds. So we now have something related to the 5-flow conjecture, and maybe the 5-flow conjecture can be attacked by some other groups than the normal ones. But I think that I should finish at 3 o'clock, so maybe this is a good time to finish. Thank you very much.
Questions? Anybody would like? Okay, so if not, we thank you very much.
Thank you.
Thank you.